Yew, and they will be presenting their paper ConFit, improving resume job matching using data augmentation and contrastive learning. Sure. Okay, seems like there's some error. So then maybe let's move on to the next paper. It's titled Unified Denoising Training for Recommendation by Haoyan, Chua. So if you're, yeah, cool.
Okay, good morning everyone. I'm Haoyan from Nanyang Technological University in Singapore, and today I'll be presenting on our paper, Unified Denoising Training for Recommendation. So there are many architectures designed for collaborative filtering that aim to understand user preferences. However, some works have shown that there are noise in user interaction data, which causes the recommender system to be unable to capture user preferences accurately. So in this table that is taken from a research paper, they trained two separate recommender systems. The first one on clean training, which excludes all false positive interactions, and the second one on normal training, which uses the entire data set. And the results showed that there's a drop in performance when these noisy interactions are included. So therefore, denoising of user interaction data is important in ensuring that the recommender system can accurately capture each user's preference, and there are multiple existing works that aim to denoise recommender systems using only implicit feedback. And this is also the focus of our paper. So there are two limitations of existing works. Firstly, existing works lacks theoretical explanation on noise in implicit feedback data and only uses empirical observations such as large loss values to determine noisy interactions. Secondly, these works treat each interaction independently of users' overall behaviors across all items and do not account for each user's overall behavior. So in our work, our contribution aims to address these two limitations. So in terms of the theoretical formulation, we actually used a Markov process to model user behavior into three different states. So preference, willingness, and action states. And in our theoretical formulation, we proved that in the second phase of taking actions based on the willingness, there's actually some form of user inconsistency where some users might be less consistent in their actions. So our denoising approach comprises of three denoising steps. So denoising the uncertain willingness, addressing how user-specific inconsistency leads to more noise and also hinders the denoising process. And our approach aims to address the limitations of existing works by taking into account user-specific inconsistencies. So firstly, to denoise the user uncertain willingness, we propose to reweigh the weights of the positive interactions through an alpha term that is negatively correlated to their loss values. And the reweighing formula is proposed as shown, where only the weights of the positive interactions are adjusted. The alpha term is a softmax of the negative loss values, so interactions with higher loss will be penalized. So next, to tackle the issue where user-specific inconsistencies lead to noisier interaction, scale-level denoising is introduced. And this method is user-specific, compared to previous methods which target the interactions only. So to change the overall weights for users with different user-specific inconsistencies, we actually introduce a beta term that negatively correlates to the user-specific inconsistency. And this beta term is obtained from a fixed uniform interval A and B, which are hyperparameters. And we first rank the users in descending order based on their user-specific inconsistency, and each user will have a beta term from an interval A and B. So lastly, to deal with how user-specific inconsistency affects whether noisy and clean interactions can be distinguished, variance-level denoising is introduced. So users with large user-specific inconsistency or careless users, even if the interactions has a low loss value, it is uncertain if it's actually a positive interaction. Whereas interactions with high loss values, it might not also be noise. So to tackle this problem, the variance between the interactions for these users should be reduced. Hence, a user-specific temperature term tau is introduced in the softmax function, which was the alpha term earlier, and an updated alpha term is used instead. So L3 is actually the combination of the two different alpha and beta terms that was used earlier, and that forms our unified denoising training. So in our experiments, we actually use 3 different data sets for our experiments: Yelp, Amazon Book, and Movie Lens. And comparing our method with the other state-of-the-art denoising methods, we are actually able to achieve better results in most scenarios across all base models. In conclusion, our paper actually analyzed noise through a theoretical perspective, which is not fully covered in this presentation. And we also propose a novel method which achieved better results compared to existing state-of-the-art denoising methods for implicit feedback. So thank you for listening, and if you have any questions, you can look for me at my poster or send me an email provided in the first slide. Thank you.
Thank you very much.